see it now. Okay, good morning. My name is Zara Haque, and I'm a junior, and today I'll be talking to you about my research entitled Development of an Efficient and Easily Applicable Low-Energy Process for the Degradation of PFAs. PFAs stands for per- and polyfluoroalkyl substances, and these are substances that are known for being resistant to both high and low temperatures, extremely resistant to degradation, and for their non-stick characteristics. PFAs are also nicknamed forever chemicals, both for their prevalence in our environment and for the difficulties associated with breaking them down. Part of their prevalence comes from the wide variety of items that they're found in. So they're found in common household items like shampoo, nonstick cookware, and fast food packaging, as well as in flame retardants, which are in firefighting foams. And that has posed a particular problem lately given the recent rise of forest fires in America. PFAs pose a significant health risk. The EPA health advisory for PFOA was 70 parts per trillion in 2016 and then was greatly reduced to 0.004 parts per trillion in 2022, really demonstrating the danger of these PFAs. PFAs have suspected adverse effects on reproduction, antibody production, and they're also suspected carcinogens. Before I delve into my own research and talk about my proposed mechanism for the degradation of PFAs, I'd like to briefly talk about the status quo and what in the world today, how we degrade PFAs. So PFAs are primarily degraded via incineration, where they're filtered out of drinking water in water filtration or treatment facilities. Then those filtered PFAs are moved to incineration plants, where they're incinerated at high temperatures for many hours. This incineration is time-consuming and also energy-consuming, and despite that, it's still not fully effective. PFAs will just simply be re-released into the air and environment via the gas coming off of these incineration facilities, and we do see increased health issues in the surrounding communities. So anecdotally, the Norlight facility in upstate New York is a PFA degradation facility where they incinerate PFAs, and people in the surrounding community have seen increased rates of both lung cancer and asthma, likely due to this exposure to PFAs. Recent literature by Trang et al. Highlights the decarboxylation of PFOA into hexadecafluoroheptane. So if we look at the structure of PFOA, which is here in the middle of my slide, it is essentially a long carbon-fluorine chain with a carboxyl group at the end. And so this recent literature by Trang et al. Removes that carboxyl group, leaving behind hexadecafluoroheptane, which is a long carbon-fluorine chain. However, this degradation is really not complete as we still have this chain left behind, and so my research seeks to move past this decarboxylation in order to fully degrade PFOA, which is a PFA that's particularly common in the state of Connecticut, and produce a decomposition process that is both less energy intensive and more time efficient, and above all, more effective. Finally, perhaps the most important goal of my project was to create a mechanism through which the byproducts of this reaction can be easily recovered and repurposed in order for this reaction to have no unusable waste. So bearing this in mind, the previous literature and also my engineering goal, I set out to design and test a mechanism through which PFOA could be fully degraded. So I combined PFOA with a solution consisting of sodium hydroxide, DMSO, and a small amount of water, put this in a Teflon round bottom flask, which was then heated to 120 degrees Celsius within a reflux system, and this reaction was allowed to run for 12 hours. The first stage of analysis of my reaction end products was of the solid end product. So as indicated by this red arrow, that's what's left behind in the Teflon round bottom flask. That's solid. So both FTIR and EDS analysis of the solid end product proved that this product was sodium carbonate. So we see two peaks on the FTIR spectra at the top of this slide, one at about 1450 wave numbers and another at about 900 wave numbers, which indicates sodium carbonate. EDS analysis corroborates this by demonstrating similar carbon, oxygen, and sodium ratios in EDS analyses of the solid end product in the bottom left and the sodium carbonate in the middle. Another interesting finding coming off of FTIR analyses of this solid end product was the disappearance of fluorine. So in this 1300 to 1200 wave number range that I've boxed in blue here, we can see the disappearance of carbon-fluorine bonds. There are three small bonds here, which are present at the 3-hour time point at the beginning of this reaction and do disappear with time. By the time we've reached 12 hours, they're pretty much gone. This is further evidenced by EDS analyses of this reaction at hourly time points. I took EDS analysis at every hour of the solid end product, and I did this for 10 hours. I then graphed the fluorine to sodium ratio of these that was shown in these EDS analyses against reaction time, and we can see that by the end of the reaction, the fluorine is pretty much gone. So this really led me to wonder and kind of think about, if the fluorine wasn't in the solid end product, where was it going? And so the logical answer to that for me was that it was in the gas. So I ran this reaction again, but I altered my procedure in order to add a gas collection tube and a balloon to the top of my reaction in order to collect the reaction headspace gas at hourly time points. And in order to ensure that I was truly getting the gas at hourly time points, as opposed to some sort of collection of the gas over multiple hours, I would leave the balloon and the gas collection tube on for an hour, take my gas sample, and then release the balloon in order to make sure that I was clearing it out every time. Gas FTR spectra of this reaction headspace really show two main things. First, we see increasing carbon-hydrogen bonds at about 3,000 wave numbers, and this is showing that the carbon-hydrogen bonds are growing because the long chain of carbon-carbon bonds is breaking, and those carbon-carbon bonds are being replaced by carbon-hydrogen bonds where the hydrogens are attaching to the terminal carbons within the breaking. And then the other thing we see is carbon-fluorine bonds, which are boxed in red here from about 1100 to 1400 wave numbers. And this is just going to show that the compounds that were in the gas contain some combination of carbon-fluorine and carbon-hydrogen bonds. So the logical next step was to use that knowledge that I had that, there was some combination of carbon-fluorine and carbon-hydrogen bonds here to identify what those compounds were. So using previous literature, like standard spectra of what perfluorocarbon compounds look like, which is here on the left, I was able to identify by comparing those to my gas FTR spectra of the gas product, I was able to identify several fluorinated carbon compounds, including specifically perfluorobutane, perfluoropentane, and perfluoropropane. The third and final finding that came out of my gas FTIR analysis was the most productive time point of this reaction. So by graphing the carbon-fluorine bond peak area from 1100 to 1400 wave numbers, which was 2 slides ago, against reaction time, I was able to see that those peak areas were the largest at about 4 hours, demonstrating to me that the reaction was at its most productive at the 4-hour time point. The third and final stage of analysis of this research was gas chromatographic analysis. So gas chromatographic analysis, essentially, if you put a gas into a GC, they are going to, those gases will elute in order from lightest to heaviest. And so my goal in doing this GC analysis was to quantitate the relative amounts of each of the fluorinated carbon compounds that I was getting out of this reaction. So here in the left-hand corner, I've kind of expanded the 4-hour time point GC, and I've done this because we have established already from gas FTR analysis that the 4-hour time point is the most productive time point, so I knew the peaks would be the biggest and the easiest to see in this 4-hour GC. And we can see pretty clearly that there are 4 distinct peaks that are occurring somewhere between 1 and 2 minutes. The C2 compound, the C3 compound, the C4 compound, and here the smallest, the C5 compound. So given that those different fragments, the different carbon fragments, had different weights because they had different numbers of carbons, they were eluting at different times. So the C2 fragment, being the lightest, was eluting first at about 1.25 minutes, C3 at about 1.35 minutes, C4 at about 1.4 minutes, and C5 at 1.5 minutes. And so with the knowledge of what minute these different fragments were eluting at, I was able to graph the release of each respective fragment over time and see at what point the release of each fragment was reaching a maximum. So in blue here at the top, I have the C2 fragment, which is reaching a peak of release at about 2 hours, C3 in green, also 2 hours, C4 in red at 5 hours, and C5 in purple at 2 or 3 hours. I also wanted to confirm that the reaction was in fact at maximum productivity at 4 hours, so I graphed the overall peak area of all 4 peaks against time, and we can see that the reaction is reaching a maximum productivity at about 3 to 4 hours. And we can also see that the reaction is over by 12 hours. So not only was my reaction reaching max productivity much sooner than the status quo, it was also over a lot sooner than the status quo. The final thing that I wanted to get out of the GC analysis was the relative amounts of each C2 through C5 carbon-fluorine compound release. And so in order to do that, I simply took the added peak area at each of those 1.25, 1.35 time points, and I added those up and put what it was for each of the C2 through C5 compounds. And so we can see that the light fluorinated carbon gases that are released are mostly the C2 fragment and the C4 fragment. So to briefly summarize what I've
just over 2 minutes left, okay?
Thank you. So to briefly summarize what I've said so far, I really have three sources of evidence of this degradation. First, I have FTIR spectra highlighting the formation of sodium carbonate as a solid end product. Second, I have gas FTIR spectra indicating the presence of fluorine-carbon bonds and carbon-hydrogen bonds, suggesting that that hexadecafluoroheptane chain was fragmenting with hydrogenation occurring at the terminal carbons, in turn suggesting the presence of light fluorinated carbon gases as the gas products of this reaction. And third, and finally, I have GC analyses which quantitate both the relative amounts and timing of release of the C2 through C5 light fluorinated carbon gases. To provide an overall big picture overview, this reaction is really occurring in two main steps. First, we have decarboxylation of PFOA, which was established by previous literature, and this decarboxylation is resulting in the creation of hexadecafluoroheptane and sodium carbonate. And third, and the novelty of this research really lies in the novel thermolysis of that hexadecafluoroheptane carbon-fluorine chain into light fluorinated carbon gases that can be easily repurposed. And I do see about 90% recovery and identification of those gases because I got about 185 milligrams at the end, and I put in 207 milligrams of PFOA. And these end products, if you'll recall from my engineering goal, one of my goals was to have end products that could be easily repurposed. And these end products really do have significant value. Sodium carbonate is a very common compound, can be used in a wide variety of items. And these light fluorinated carbon gases range in price from about $5 to $1,000 per gram. And they have value in various industries. They can be used as refrigerants, blend components for commercial refrigeration and AC systems, fire extinguishing agents, and they even have pharmaceutical applications as propellants. The third end product of this reaction is really a PFA-free environment, which is simply put priceless. In terms of implementation of this research in the real world, my proposed mechanism is faster, reaching its peak productivity at about 4 hours as opposed to 24 or even more than that with incineration. It's low energy, occurring at about 120 degrees Celsius, which again is in stark contrast to the heat required for incineration, and it's easily applicable. We really need minimal resources to do it: DMSO, sodium hydroxide, and a relatively small amount of water. The
All right,
products coming
Zara,
off of
your
this.
time is up.
Okay, thank you.